In a previous video, we looked at polynomial rings, and we showed that over an integral domain, its polynomial ring is also an integral domain. But in fact, that's not enough to give us all of the structure that we really want. We have to have the ground ring be a field in order to get some kind of nicer structure, which puts polynomials kind of on the same level as integers. So, and that is exhibited by this division algorithm for polynomials. So let's let little k be a field and f of x and g of x be polynomials with coefficients in that field. In other words, they're in the polynomial ring k adjoin x. Then there are unique polynomials q of x called the quotient and r of x called the remainder, such that f of x equals g of x times q of x plus r of x. Then we have the degree of r of x is bigger than or equal to 0, and it's strictly less than the degree of q of x. So before we get started, I want to look at a couple of examples. And the first example that I want to look at is actually in N, just to give you guys kind of like a parallel between the division algorithm in numbers. So let's notice that we can do the division algorithm with maybe the number 11 and the number 3. We can write 11 as 3 times 3 plus 2. Great. And then notice that here we have 2 is most definitely between 0 and 3. So here where this is our quotient and this is our remainder. Now the next thing I want to do is give an example with polynomials. So let's do the division algorithm. With, let's say these are our two polynomials. 4x cubed plus 2x squared plus x plus 3, and then 2x plus 1. Okay, so unfortunately, there's not a great way to do this quickly. It's just kind of a bunch of high school algebra type stuff. There's also a way to do this in Mathematica, but I'll let you guys look that up if you want to. So we need to do 2x plus 1 is dividing into 4x cubed plus 2x squared plus x plus 3. Now we need to look at the leading coefficient here, 4. We want to say, okay, well, what do I need to multiply to 2x plus 1 so that this 2x term turns into a 4x cubed term? And that is going to be 2x squared. So that's going to get the leading terms to match up. And then notice, if we multiply this guy onto both of these, we're going to get 4x cubed plus, and then this times this is going to be 2x squared. And now we need to subtract this whole thing. That's going to give us a remainder of, that's going to give us 0 as we subtract. Now we bring this guy down. That's going to give us plus x plus 3. Okay, great. Now we look at the leading coefficient here, and the leading term here, and we say, what do I need to multiply by 2x to make it into x? And that's going to be a half. Great. And that's going to give us a x plus 1/2. As we move it down here, we need to subtract that. And notice that's going to give us a 3 minus half, which is 5 halves in the end. So what all of this tells us is that 4x cubed plus 2x squared plus x plus 3 can be written as 2x plus 1 times 2x squared plus half plus 5 halves. Great. So here we have this guy is our quotient, and then this guy is our remainder. Our remainder happens to be just a constant in this case, but that's actually important because notice the thing that we're dividing by is of degree 1, so our remainder has to be of degree 0. Okay, I'll clean up the board and then we're going to do this proof. In an example, so now let's go about doing the proof. So let's go ahead and suppose we've got two polynomials within this polynomial ring with coefficients in the field, and we'll call those f of x and g of x, and let's say that the degree of f of x equals n, and the degree of g of x equals m. Great. And then let's go ahead and also suppose that m is less than or equal to n. Because notice the other case is pretty boring, and maybe let's sketch that out real quick. So why are we making that supposition? So otherwise, m is strictly bigger than n, and then we have the following equation. So f of x equals 0 times g of x plus f of x. And then notice that the degree of f of x is less than the degree of g of x. So in other words, we can take our remainder just to be kind of our original function. So there's nothing really going on here. Our quotient is 0. So if our degrees are kind of reverse of what we should have, our quotient is going to be 0, and this isn't super interesting. Okay, I'll erase this yellow and then we'll get going with the real proof. Okay, we've argued why the only interesting case is when m is less than or equal to n, and we're actually going to proceed by induction. And the way you want to think about it is like this. N is equal to m plus k. So we're like moving that k up. So our base case is going to be obviously the k equals 0 or the m equals n case. Okay, good. So in other words, we can write f of x as a n x to the n plus all the way down to a0, and g of x is equal to bn x to the n all the way down to b0. We know they have the same degree, so we can use the same index there. And furthermore, since they have that degree of n, we know that the leading terms cannot be 0. Great. Now the next thing that we can notice is that if we have two terms with the same degree, it's actually pretty easy to form this quotient remainder relationship, and we can do that in the following way. So notice we can take f of x equals, now if we multiply g by a of n over b of n times g of x. Okay, so this base case is a little bit tricky, but if you see the trick, it's not so bad. So what we're going to do is start with f of x, and we want to write f of x as something times g of x plus a remainder. But notice the thing that we'll multiply by g of x is just a constant because we don't want to raise the degree at all. And we want to multiply g of x by something so that this coefficient turns into that coefficient an. And so the way to maybe do this cleanly is just to start with f of x equals f of x, and then we're going to add and subtract the same thing. So here we'll add in an over bn times g of x, and then we're going to subtract an over bn times g of x. Okay, so now why would we do that? Well, notice this guy right here starts off like an x to the n plus lower terms, which means this guy starts off the same way, an x to the n plus lower terms. And how do we know that? Because we're multiplying bn by an over bn, so that's obviously a sub n. Okay, good. Now, notice that we can reorder these things a little bit. We have an over b to the n, so this is playing the role of our quotient, our q of x, times g of x, plus this quantity right here, f of x minus an over bn g of x. Great. And now this guy right here is playing the role of the remainder. Now we just need to check that the remainder has the correct degree. It should have a degree of less than n, but it does, because notice f of x starts off with an x to the n, and then this term also starts off with an x to the n. So that means this thing is going to start off with something like a sub n minus 1 minus an over bn b sub n minus 1 times x to the n minus 1 and lower terms. You can get a real handle on exactly what that looks like, but it doesn't really matter. And so, in other words, what we have here is the degree of r of x is most definitely strictly less than n. So that means we've established this division algorithm in the base case. In other words, in the case when k is equal to 0. Okay, I'll clean up the board and then we'll move on to the next part. Okay, we've done our base case. Now we're ready to make our induction hypothesis. So what we're doing is we're supposing that the degree of f is n and the degree of g is m. And for our hypothesis, we'll suppose for all p of x with the degree of p of x is strictly less than n, we can do the division algorithm. So this is an example of strong induction, which strong induction is equivalent to standard induction. So that's something you can find probably at the very beginning of your textbook. Okay, great. So the next thing that we want to do is consider this following polynomial. So what we want to do is tweak f to make it have a smaller degree and then apply this induction hypothesis. That's kind of our strategy. So let's consider this polynomial. I'll call it f hat of x, just to notice that it is related to f of x. And it's defined by f of x minus a n over bm x to the n minus m times g of x. Okay, so let's see what that looks like. So I'm going to use this standard notation that we had on the last board. So f of x is going to be a sub n x to the n plus lower terms. And from that, we're subtracting a sub n over b sub m, x to the n minus m, and then recall that g of x was b sub m, x to the m, plus lower terms. Great. But now we can distribute this guy through, and notice distributing that guy through will give this highest term degree of n. So when we add these things together, notice we'll have a sub n minus a sub n over b sub m times b sub m will be our coefficient of x to the m. X to the n plus lower terms. Now I'm going to start giving a name for those lower terms. So I'll say a sub n minus 1 hat, x n minus 1, all the way down to a sub 0 hat. And I should say that those hats are related to the original coefficients after we've subtracted this thing out. But now notice this part is like very, very clearly 0. So we have f hat of x equals a sub n minus 1 hat x n minus 1 all the way down to a 0 hat. In other words, f hat of x is degree strictly less than n. Okay, great. So I'll clean up the board and then we'll keep going. Okay, so let's just reiterate where we are so far. So we were proceeding by induction. We showed that this division algorithm is easily possible when the degree of the two polynomials is the same. Then we made an induction hypothesis that said for all polynomials of degree less than n, this is possible. Okay, and then we have f of x is a degree n polynomial, starting with a n x to the n and descending. And g of x is a degree m polynomial, starting with b m x to the m and then decreasing. And then we formed this object f hat of x, which is f of x minus a sub n over b sub m x to the n minus m times g of x. And we renamed those coefficients a hat n minus 1 x to the n minus 1 and decreasing. And we also argued why that thing has degree strictly less than n. So now what we want to do is apply the induction hypothesis to f hat of x and g of x. So let's recall that our induction hypothesis was that we could do the division algorithm if we got the degree lower than n. So that means what we can do is write f hat of x equals g of x times q hat of x plus r hat of x. And here we have the degree of r hat of x is less than m, which is the degree of g of x. Okay, great. So now what we want to do is re-ravel this hatted equation back into an equation that involves just f instead of f hat. So let's see how that'll go. Okay, so now what we'll do is start with f of x and rewrite this equation that defined f hat of x in terms of f of x. So that means we've got f of x equals f hat of x, and then plus a sub n over b sub m x to the n minus m times g of x. Okay, now we're going to insert this application of the division algorithm into this equation for f hat of x. So let's see what we get for that. This is going to be equal to g of x times q hat of x plus r hat of x plus a sub n over b sub m x to the n minus m g of x. So the next thing that we can do is go ahead and combine these two things together, because notice they both have g of x as a common factor. So that's going to allow us to write this thing as g of x times the quantity q hat of x plus a sub n over b sub m x to the n minus m plus r hat of x. But if we rename this guy right here just plain old q of x, that can play the role of our quotient. And furthermore, since the degree of r hat of x is strictly less than m, this r hat can still play the role of our remainder. So we're good to go on that as well. So now let's go ahead and read the extreme left and right hand side of this. Notice we have f of x is equal to g of x times q of x, where I'm writing q of x as the combination of those, plus r hat of x, and r hat of x has the correct degree rule. In other words, we have this division algorithm output satisfied by f and g. Okay, so that completes the proof of this part of the theorem. The next thing that we want to do is prove this uniqueness, which is actually more important than you might think. Okay, now we're ready to prove uniqueness of this result. So let's say we have f of x equals g of x times q1 of x plus r1 of x, and then f of x also equals g of x times q2 of x plus r2 of x, where both of these remainders have the property that their degrees are less than the degree of g of x. Okay, so in other words, what we're saying is that the quotient and the remainder may not be unique in this division algorithm setup. Now what we want to do is go ahead and subtract these equations together to see what happens. So notice if we subtract these equations, we're going to get 0 equals g of x times the quantity q1 of x minus q2 of x equals plus r1 of x minus r2 of x. So that's what we get if we subtract these two guys. But the next thing that we can notice is we can move some things around here, and that's going to give us r2 of x minus r1 of x equals g of x times q1 of x minus q2 of x. Okay. Now let's look at the degree of both sides of this. So notice that if we take the degree of the left-hand side of this equation, we're going to get the degree is less than the degree of g of x. Okay? But then if we take the degree of the right-hand side of the equation, well, we're multiplying g of x by a new polynomial. So that means the degree of this thing is strictly bigger than the degree, bigger than or equal to the degree of g of x. And you might say, well, why is it not strictly bigger? Because this could be a constant polynomial over here. So what we have is we have the left-hand side is simultaneously less than the degree of x and bigger than or equal to the degree of x. But what that tells you is that the left-hand side of this equation has to be 0. So 0 is the only polynomial that kind of has all degrees. So in other words, the left-hand side of this equation is 0, but that implies the right-hand side of this equation is 0. But since g of x is not 0, because it doesn't make sense to divide by 0, that tells you that q1 minus q2 is 0. In other words, we have r1 of x equals r2 of x, and q1 of x equals q2 of x. So we have proven the uniqueness of this quotient and remainder.